Hi everyone, my name is Karan Bangsraz. Today Team LMA will be presenting our group FYP project, the Tadris Explorer for Real-Time System Monitoring. The presentation will be broken down into the following chapters, starting with introductions and overviews, and finally a demonstration of the system, followed by a reflection of the entire project. Now, I will introduce the members of our team. Gavin Austin has worked on many different software engineering projects in his 4 years of being a software developer. Both managing a team and being a reliable team member, this experience and his creative approach to system design made Gavin the clear choice for project manager and back-end lead. Isabella Andrews has a very strong communication and people skill, allowing her to resolve conflicts within and across teams. Her organizational skills are unparalleled. She has a precise knowledge of all business requirements of a project, being able to compose accurate and high-quality documentation with ease. For these reasons and more, Isabella was the perfect member to be this project's team liaison and business analyst. Norman Meningo has been working as a DevOps member for the University of Newcastle for a few years prior to this project. He also possesses exceptional writing and record-keeping skills. His experience made him the perfect choice for his roles in this project. As for me, I have spent 2 years as a front-end software developer. This and my keen eye for detail allows me to produce work of the highest quality, making me ideal for my roles as front-end lead and quality assurance. Now, I will introduce our client. Our industry partner is Lockheed Martin Australia. They are a global security and aerospace company and are a wholly owned subsidiary of the Lockheed Martin Corporation. Lockheed Martin Australia are one of the largest suppliers of technology and training to the Australian Defence Force, including, but not limited to, guided weapons, naval aviation combat systems, and space domain awareness. Our client liaisons for this project were Greg Mitchell, LMA RMS Deputy Chief Engineer, and our primary supervisor and contact. Alex Tolnai is a computer systems architect and our project's technical advisor. And finally, Scarlett Pollock, Engineering Project Manager Associate, and our secondary supervisor and point of contact. Lockheed Martin Australia has reached out to the University of Newcastle in dire need of an elite team of software engineers to design, build, and deploy a robust, scalable, and highly customizable status monitoring system for network-connected devices, with the main feature being retrieving and delivering real-time device information within a 30-second window. This system needed to seamlessly interface with the existing equipment housed within Lockheed Martin's Tactical Air Defense Radar System Processing Cabin, also known as TADRIS. This would ensure minimal operational disruption. Our system was built using open source solutions to reduce project budget whilst having plenty of documentation to refer to during development. The success of this project is also an indicator that open source solutions are a viable option when developing military projects. Our system also needed to be easier to use than Lockheed Martin's existing strategies. Designing an intuitive user interface and allowing for additional devices to be added as required were critical to the success of this project. However, due to the sensitive nature of the equipment our system needs to connect with, no additional details regarding the TADRIS processing cabin itself will be explored. Only our system and the specific network devices will be covered in this presentation. Now I'm going to talk about the objectives in a little bit more depth. Firstly, the ROG color codes. The system would use red, orange, green color codes to indicate device status at the system level, providing clearer insight for users as to where issues are occurring. The subsystem access. The system would allow access to the health status of specific devices, subsystems, or components for error or alert notifications. Since users can access the subsystem information within 3 clicks, this not only provides a user with detailed information, but also enhances user navigation. Next, real-time updates. The system would detect and display status changes within 30 seconds of the actual status change. This objective was met through implementing a heartbeat scan every 30 seconds to ensure the status changes are displayed within 30 seconds of a live update. The team built high-fidelity prototypes to ensure that critical functional features were properly implemented. Features such as data collection, integration with ROG codes, error handling, network connectivity, and security features that aligned with ASD Essential 8. User interface prototypes were also developed to showcase the following features: hierarchical interface with ROG codes, real-time updates, accessibility and usability, a notification system, reporting and analytics, search and filtering functionality, and a responsive design. Device demonstrations were an indicator of progress made over the duration of the project and meant to inspire confidence in our ability to deliver. In turn, we delivered a system that could monitor more than one network-connected device. Lockheed Martin Australia has a big emphasis on using the ASD Essential 8 when making any decisions for any aspect of a project. This extended to Team LMA's project, and we followed in suit. For all business and development decisions, we constantly referred to the ASD Essential 8. This ensured that we not only complied with LMA's policies, but it provided a constant security-orientated mindset, critical when handling any sensitive data. When working with large systems, there is bound to be disaster, and every engineering project must implement some forms of disaster recovery and redundancy strategies. So Team LMA implemented the following: verbose logging, UI warnings, and email notifications in the case of alerts or errors. On the project completion, where the system is delivered, users must be able to know how to use the system, and developers who wish to maintain and extend the system must know how the system works. To address these needs, Team LMA has developed countless documents detailing the system's architecture and operations, as well as a user guide outlining all the features and steps on how to perform them. Team LMA has promoted accessibility through the following: ROG color codes, which ensure a device status is very clearly understood. Any buttons within the app clearly explain their functions with labels, and using a standardized web application layout, which allows for intuitive ease of use. I will now hand off to Norman Meningo, our DevOps lead and secretary.
A variety of research topics were looked at as related works when developing the project. With connected devices, Team LMA investigated the communication methods with WMI objects and possible ways to remotely collect health information of Windows servers. Team LMA explored how asterisk messages are developed and transported throughout the network and looked at possible implementation strategies to support this communication. Research was also done for SNMP and Modbus devices, looking into implementation methods achievable with the project resources at the time. Additional research was also conducted on how devices communicate over the Ethernet and the different ways that this can be applied to the project. Team LMA researched possible front-end, back-end, and database management solutions for the project. Team LMA investigated both the Angular framework and Grafana for possible front-end solutions, looking for the pros and cons of both implementations. Due to limited support for dynamic integration, Grafana was not implemented in the final build. However, the system currently utilizes Angular framework as the front-end solution. Team LMA investigated the utilization of .NET 7 as a potential back-end solution. .NET 7 offered vast amounts of accurate documentation and applicable features, alongside a large community backing that proved detrimental to the development process. Currently, .NET 7 is utilized as the back-end solution for the project. Finally, Team LMA looked at implementing MySQL as a database management system for the project. MySQL was chosen for its reliability, scalability, and open source nature, making it the preferred option for not only this project, but also many other applications. Team LMA also looked at virtual machines as potential project environments at the time, as a virtual machine offered flexibility, resource isolation, and the ability to run multiple operating systems on a singular device. Team LMA was able to set up Windows and Linux virtual machines. Team LMA also investigated setting up virtual networks to simulate expected environments. These environments were removed as they began to introduce more complex issues to the project, limiting the time available for the development of a successful product. By looking at these topics, Team LMA was able to develop a better understanding of available resources and how they can be used throughout the project. The main topics researched are the connected devices, possible implementations for front-end, back-end, and database solutions, as well as the potential project environment that can be used to develop emulators for testing and development environments.
As part of the background research conducted in this project, Lockheed Martin supplied us with a series of documents that outline the system and use cases that we'd need to integrate with. In addition to this, we received a reference table that defined the interface that each piece of equipment used to communicate on the network. Among these interfaces were a variety of different standards, such as Asterix, a standard used in aviation for the exchange of weather information and data, WMI, a set of tools and standards developed by Microsoft for managing and monitoring window-based systems, Modbus, which is a protocol initially designed for serial communication, and SNMP, a widely used network protocol for monitoring and managing network-connected devices and systems such as routers, switches, and servers. Among these documents was a diagram of required equipment that represented the declassified areas of the TADRIS processing cabin. This cabin contained a series of devices such as ECU controllers, servers, power monitors, and distribution units that all connect into a single network ecosystem.
Team LMA looked at utilizing many principles from a range of project methodologies. Agile development principles emphasize customer collaboration, adaptive planning, continuous improvement, and iterative development. Agile development principles were employed throughout the duration of the project to foster a flexible and customer-centric approach to the software and product development. Iterative development was applied by breaking down the sprint goals and developing manageable tasks for continuous building and refinement of the product. Regular feedback cycles were conducted in the form of fortnightly client meetings, weekly team meetings, and frequent code reviews. Incremental feature implementation was utilized throughout the development process to ensure smooth and efficient integration of required functionalities. Applying agile development principles resulted in improved team collaboration, faster response to changing requirements, and higher customer satisfaction, as well as the delivery of a high-quality product in a more efficient and adaptive manner. The Scrum is a widely used agile framework that provides a structured approach to project management. The Scrum framework was utilized in the project to emphasize iterative development, frequent inspection, and adaptation, with a focus on collaboration and delivering valuable increments of work. Collaboration and frequent inspection was achieved in the form of peer programming sessions, weekly team meetings, and routinely code reviews. The group successfully displayed increased adaptability by regularly reviewing their progress during the sprint retrospectives and making continuous improvements to their processes based on feedback and changing project requirements. Scrum ceremonies facilitated effective project management and progress tracking. These ceremonies included daily stand-up meetings, sprint plannings, and sprint reviews. Implementing the Scrum framework streamlined the project management, enhanced team collaboration, and provided the team the ability to better adapt to changing project demands, as well as the consistent delivery of increment works, ultimately improving the overall project efficiency and quality. Test-driven development is a software development approach where the developer writes tests before writing code, ensuring that the code is fairly tested and meets the requirements, resulting in higher code quality and reliability. Testing was conducted frequently throughout the development of the project, ensuring the reliability and quality of the codebase. Through test-driven development, the team was able to identify and rectify issues early in the development process by writing tests before developing the features. Task tracking and document management are vital components of efficient project development. Task tracking and document management was conducted at least once a week per team meeting using the project collaboration and management tools. Documentation and tasks were tracked to determine any progress or blockers and discuss future work. By implementing task tracking and document management, Team LMA ensured that team members can collaboratively manage tasks, access relevant project documents, which is crucial for maintaining organization, transparency, and accountability throughout the project lifecycle. The team also tracked tasks and documents to guarantee that document standards were maintained throughout the project, ensuring that all aspects relevant to the project were captured as per LMA and UON standards. Team LMA utilized a set of project tools to ensure that the project methodology principles and effective project management strategies are followed in order to develop a higher quality end product. Zoom is a versatile and user-friendly video conferencing platform that enables seamless communication and collaboration for project development teams, offering features like virtual meetings, screen sharing, and file sharing to enhance remote work and team coordination. Using Zoom allowed for regular meetings and reviews to be conducted with stakeholders, including representatives from LMA, to gain more insight and feedback on the current project, ensuring that the project is progressing in the right direction. Meeting notes were taken after every meeting to record action items and feedbacks from the LMA representatives. Discord is a popular communication platform primarily used by gamers, but also increasingly embraced by various communities and organizations. Discord was the main tool used for in-project communication within the team to schedule and support team meetings and discussions. Meeting notes were taken during weekly meetings to ensure that the action and communications have been recorded. Using Discord offered a real-time voice, video, and text chat to facilitate efficient and interactive communication within the team, both with casual and professional settings. Jira is a powerful project management and issue tracking tool that enables teams to plan, track, and manage their work efficiently. Jira was the project management tool utilized in this project for assigning all software development tasks and establishing fortnightly sprints and goals. Jira provided real-time insights and collaborative capabilities that assisted in streamlining the development pipeline and boosting productivity within the project. Confluence is a versatile collaboration platform that empowers teams to create, share, and collaborate on documents, ideas, and knowledge in centralized space, facilitating seamless communication and information sharing to enhance productivity and decision-making. Confluence was used in this project as a shared space to store all documentation provided by LMA, as well as fortnightly and weekly meeting minutes. BitBucket is a version control platform designed for software development teams. BitBucket's key advantages included robust version control, seamless code collaboration, built-in CI/CD, enhanced security features, and both cloud and self-hosted deployment options, making it a versatile and comprehensive platform for software development teams. BitBucket provided the project with Git and Mercurial repositories for source code management, along with tools for continuous integration and collaboration, enabling the project developers to work together seamlessly and efficiently on the software project while ensuring code quality and security. OneDrive is a robust cloud storage and file sharing platform developed by Microsoft, allowing users to store, access, and share their documents, photos, and files securely from any device with an internet connection. OneDrive was used in this project as a restricted online file storage system to store and develop main deliverables such as project plans and reports. The use of OneDrive provided a familiar environment for developing these reports and projects, as well as proving a great means to enhancing data accessibility and collaboration within the team across the different devices. In-person communication is the art of conveying ideas, emotions, and information face-to-face, fostering genuine connection, trust, and nuanced understanding through direct interactions, making it an invaluable tool for effective development and relationship building. In-person communications were conducted frequently throughout the project for more impactful discussions and extensive meetings, especially those related to project milestones and requirements. In-person communication allowed the group members to have a higher engagement, better retention of information during meetings, which is vital to the project's success. The execution of the project was characterized by collaboration, adaptability, and a commitment to delivering a higher quality solution. With the diverse skill set, the team composition enabled effective problem solving and innovation. The project balanced flexibility and structure by combining agile principles and Scrum framework, ensuring the objectives were met efficiently and effectively. Frequent feedback loops, collaboration tools, and robust documentation practices contributed to the project's success, enabling the team to deliver a robust and efficient status monitoring system.
Introducing Tadris X, a real-time system monitoring product designed to reduce the overhead involved in operating and maintaining the uptime of the Lockheed Martin Tactical Air Defense Radar System. TARDIS X has many features, including a focus on security. User security roles dictate who can access and manage specific system features, enhancing security by restricting permissions to unauthorized personnel. AES encryption of sensitive data provides a high level of data security by transforming sensitive information into a format that is exceptionally challenging for unauthorized parties to decipher. Argon 2 password hashing, combining with Assault, fortifies user password security by making it computationally intensive and resistant to brute force attacks. Interactive device graphs provide a visual and user-friendly way to monitor and analyze real-time data trends, facilitating informed decision-making for the network optimization and management. Device status logging records and tracks the history of device activities and errors, offering valuable insight for troubleshooting and network maintenance. ROG status colors offer a quick and intuitive method for assessing health and status of network devices, simplifying monitoring and issue identification. Device grouping streamlines the management of multiple devices by allowing similar devices to be seen using one status indicator. Dashboard preferences enable users to tailor their monitoring dashboard to display the specific device types that they oversee. In-app alerts deliver real-time notifications within the application interface, ensuring users to stay informed of crucial events while monitoring the platform. Uploadable configurations simplify device management by allowing bulk application of customized settings, ensuring consistency and reduced manual configuration efforts. Real-time device updates ensure that any errors or warnings that occur on a device attached to the system are seen immediately and not left until something major occurs. Uploadable system settings offer flexibility by enabling the customization of the platform parameters to align precisely with specific requirements and preferences. Real-time communication and status monitoring. Here we can see a sped up version of the system showing that as the device sends data through, the interface updates, keeping any person monitoring the system in tune with the exact current status of every device. Currently this works for both the WMI and Asterisk devices, as we see here, where the time series graph that represents each part of the message updates and moves as a new message has been shown. Device administration. All devices that are configured within the system are given a group. Groups allow administration staff to see a collection of devices that are similar and require one type of engineer to triage any issues. Selecting a group brings the staff member to a page that shows an individual device level overview. From there, they can then select each specific device to see a more low-level overview of exactly what has caused an issue. Navigating back to groups that this device is in is as simple as clicking the tag above the device status. Devices can be in multiple groups, and groups can have multiple device types. user roles and system administration. TardisX supports 3 main user roles. Here we have an overview of what a read-only user can see. This allows a non-technical staff to get a baseline understanding of the current status of a system. This can include, if they choose, to look at logs and data from specific devices. However, the normal level of triage would be to take this information and contact a more technical engineer to investigate further. This level user only has access to the 3 main levels, being dashboard, group overview, and individual device log. When navigating the dashboards, users can zoom and move data as they see fit to get a better indication of current status. As we can see here, the user role has a user profile page and can be accessed from the left-hand menu. On the home page, this level user also has direct access to devices that are in error, as well as devices with warnings. From the user profile page, a user can update which device types they would like to see on their home page and also reset their password. It is important to note that there is nothing taken away from the user at this level, only additional to that of read-only. System admins have a configuration upload page where they can load general configurations such as which email the alert goes to, but also more importantly, device configurations. This is what loads devices into the system, applies groups, and applies the whole suite of network monitoring. Once an admin has applied a group, all the devices stay in a warning state until their next communication. Device configurations are uploaded in a JSON file, which includes all the major data that the system needs to talk to that device. Once a configuration has been uploaded and applied, the device, including the device groups, is instantly represented on the dashboard. Alerts and notifications. As the system detects errors and warnings, in-app and email notifications are sent to those parties that need to address. Here we can see that selecting an alert takes the user directly to that device. Email notifications provide just a simple message letting the user know what has happened. API and extendability. The TardisX Explorer system has an API that is available for developers to expand the system into other tools. All of the backend endpoints are secured by user role using a bearer token in the request. Limitations. The largest limitation of our system is in regards to the device types that can be monitored. Currently, only WMI and Asterisk devices can be equipped with the system. The main reason why these limitations occurred was timing and availability of equipment. These 2 device types only cover a fraction of total devices in the Tatra system. Despite this, it still provides a sound base for the extended development of this system. This limited scope restricts the system's ability to provide a holistic view of the entire network. However, for the currently implemented device types, this system provides an excellent user interface with great usability.
This section marks the culmination of months of hard work, dedication, and innovation as we reflect on the system delivered and provide a comprehensive review of the overall project. Our journey began with a clear mission: to develop a proof of concept status monitoring system for network devices within the Tactical Air Defence Radar System processing cabin. Our objectives were clear: provide real-time monitoring, seamless integration with existing infrastructure, and promote cost-effective open source solutions. The status monitoring system we've created embodies these objectives, offering sub-30-second device health status updates, customization options, and real-time monitoring of network devices. The system we've delivered not only meets our goal of providing a high-quality, minimum viable product, but also serves as the foundation for enhancing operational efficiency and reducing downtime for critical equipment. Our project execution was guided by a skilled and multidisciplinary team leveraging Agile and Scrum methodologies. Collaboration tools, test-driven development, continuous integration, and regular feedback loops were integral to our success. This approach allowed us to maintain flexibility while delivering a high-quality solution. Expected versus actual outcomes. We set out to meet specific objectives and stretch goals, and I am pleased to report that we largely succeeded. From implementing ROG color codes to delivering a functional demonstration with multiple devices, we met or exceeded our expectations in most areas. ROG color codes and definitions. Our goal was to use ROG color codes for device status, and we successfully implemented this objective. The further development of detailed ROG code definitions was deemed a lower priority due to time constraints. However, it's an area for potential expansion and improvement. Multiple device integration. Our original goal was to showcase one device in our demonstration. However, despite setbacks, we exceeded this goal by delivering a functional demonstration featuring 2 network-attached devices, highlighting our steadfast commitment to quality throughout the system's development. High-fidelity prototypes. We aimed for high-fidelity prototypes with features like data collection, ROG code integration, error handling, and security aligned with ASD Essential 8. The system effectively includes these features, though further user testing could enhance areas like responsive design and accessibility. Cybersecurity assessment. Regarding cybersecurity, we aim to implement the ASD Essential 8 elements related to software and software engineering. I'm thrilled to report that we achieved this objective seamlessly, aligning completely with our cybersecurity goals and ensuring the robustness of our system. Throughout our journey, we have yielded significant achievements, often exceeding our expectations, and we're excited to share these outcomes. Project milestones and schedule. Our project adhered to a carefully crafted timeline marked by key milestones that guided our progress. However, the timely acquisition of resources is imperative for any project success. Regrettably, we encountered delays in procuring essential resources, including necessary hardware and vital customer-supplied data, especially during the discovery phase. These unfortunate setbacks impacted our pace of progress, and the absence of clear instructions posed additional challenges throughout the project. Nevertheless, our team displayed adaptability and unwavering commitment to delivering a high-quality solution within the revised constraints. Lessons learned. Team LMA's journey throughout this project has been a rich source of valuable insights and lessons, each contributing to a deeper understanding of software engineering, teamwork, and project management. We recognize the significance of reflecting on these lessons, as they serve as guiding principles for continuous improvement in future endeavours. Adaptability is key. The ability to adapt to unforeseen challenges and changes in project dynamics is paramount. Our experience with the delay and eventual cancellation of customer-supplied data underscored the importance of flexibility in adjusting plans when circumstances demand. Clear communication matters. Effective communication within the team and with stakeholders is fundamental. We've learned that ambiguity in instructions and lack of clarity from external sources can lead to confusion. Proactive and clear communication is essential to keep everyone aligned. Thorough planning is essential. Comprehensive planning lays the foundation for success, especially in the early phases. To mitigate potential issues, we realized the importance of thorough project planning, including risk assessment and contingency planning. Testing and validation are continuous. Continuous testing and validation are integral to software development. Our journey has highlighted the significance of robust testing procedures to identify and rectify issues early, ensuring the quality of the final product. Team collaboration is invaluable. Effective collaboration within the team fosters creativity and problem solving. Our project reinforced the importance of open communication and a collaborative spirit to overcome challenges and drive innovation. Client engagement is a two-way street. Client engagement and involvement in the project are essential for mutual understanding. We've learned that maintaining a close relationship with clients can lead to better project outcomes and satisfaction. Time management is critical. Time management is pivotal in project success. Our experience underscored the importance of adhering to schedules and timelines, especially when adjustments are needed due to unexpected delays. Document everything. Documentation is an invaluable asset throughout the project lifecycle. We've come to appreciate the importance of meticulous documentation, which aids in knowledge sharing, problem solving, and project continuity. Learn from challenges. Challenges are opportunity for growth. Overcoming obstacles and setbacks can improve problem-solving skills and provide a deeper understanding of project complexities. Stay committed to quality. Quality should never be compromised. Our project reinforced the idea that delivering a high-quality product is paramount, even when facing constraints and challenges. These lessons have not only enhanced our project management and software engineering skills, but also provided valuable insights to navigate future endeavours more effectively. Team LMA is committed to applying these lessons to improve project execution and consistently deliver exceptional results. Reflecting on our accomplishments and lessons learned, we look forward to future endeavours with a renewed commitment to excellence and innovation. Reflection on future system extension. As Team LMA concludes the primary phases of this project, we recognise the importance of looking ahead to the future. Now we explore potential extensions and enhancements for the status monitoring system we've diligently developed. While we've successfully met the project's objectives and even exceeded some, we believe there's always room for growth and evolution. These future system extensions hold the promise of further enhancing the system's capabilities, expanding its reach, and ensuring its continued relevance in an ever-changing landscape. Now let's delve into the potential future extensions we've identified for the system. These extensions aim to address emerging needs, improve user experiences, and bolster the system's effectiveness. Predictive alerts. Leveraging historical data and advanced analytics to predict and alert users about likely future events or issues, enabling proactive problem resolution. This minimizes downtime, enhances system reliability, and improves performance by addressing potential problems before they impact operations. Improved data visualization and customization. Enhancing data visualization for interactivity, informativeness, and user-friendliness, empowering users to extract valuable insights quickly. This facilitates more informed decision-making through advanced data visualization techniques and the capability to customize user views easily. Extended device demonstration. Expanding device demonstration capabilities, including SNMP and Modbus integration for status monitoring and showcasing the system's adaptability. This demonstrates system versatility, compatibility with various devices, and its ability to provide a comprehensive view of infrastructure. These potential extensions signify our commitment to continuous improvement and a user-centric approach to system development. By prioritizing these extensions and considering our recommendations for future development, the project can continue to evolve and meet the changing needs of its users effectively. In essence, the success of these future system extensions is pivotal to the long-term success and sustainability of the project. By embracing these opportunities for growth and improvement, the project can remain at the forefront of device status monitoring within the Tactical Air Defence Radar System, Processing Cabin, and overall Lockheed Martin Australia landscape, delivering value to its users and stakeholders alike. On behalf of Team LMA, I want to extend our heartfelt gratitude to all those who have been a part of this journey. Our thanks go to our project stakeholders, Lockheed Martin Australia, for their support and collaboration throughout the project. We also extend our appreciation to the University of Newcastle for providing us with valuable resources and guidance. A special thank you to our dedicated team members who have worked tirelessly to bring this project to fruition. Your hard work, creativity, and unwavering commitment have been the driving force behind our success. Last but not least, we express our gratitude to our mentors, advisors, and all those who have contributed their expertise and insights, helping us navigate the complex landscape of this project. As we look towards the future, we are excited about the potential for further growth and development of the LMA status monitoring system. The lessons we have learned and the recommendations we have made will undoubtedly guide future endeavours, ensuring continued success and innovation. Thank you all for your support and for joining us on this journey of discovery and achievement. Together we have laid the foundations for enhanced operational efficiency, and we look forward to the continued evolution of this system to meet the ever-changing needs of its users and stakeholders.